Hello everybody, we have seen concepts of optimal control and also seen concepts of estimation, especially Kalman filter and some extended Kalman filter and uncentered Kalman filter, things like that. And now we will migrate to a slightly advanced topic in aerospace engineering, of course, which talks about integrated estimation, guidance and control. That means all these concepts that are available, bits and pieces, estimation itself, guidance itself and control itself, can we really talk some sort of in a integrated fashion and then try to get some advantage out of it actually. So, the next couple of lectures I will talk about that at various levels and things like that, and primarily these are out of our own research actually. So, some of the references will be our own publications as well. Okay. Let us get started. So, this motivation and philosophy is like this. What you are interested is to fuse the estimation, guidance and control loops at various levels, and benefits arise because of the fact that integrated design approaches are capable of retaining and exploiting the synergy between various subsystems. So, ultimately it is finally one system. So, if you separate it out and then put estimation as a subsystem, guidance as a subsystem like that, and ultimately everything has to act on the same system finally, and then if you do not exploit the synergy between them, then unnecessarily there are transient effects, there are large delay effect, things like that actually. So, can we kind of suppress some of those by invoking some of these concepts actually. So, the integrated design approaches proposed in literature can be broadly classified into two groups, okay, and primarily it is integrated guidance and control or integrated estimation and guidance. Now, there are also concepts of integrated guidance, control and estimation together, and popularly it is IEGC some people call, and some people call as IGC and E. Okay. So, integrated guidance, control and estimation actually. So, depends. Anyway, so the concept is more important. So, let us see what is going on here. So, typically when you, and these are largely in the context of missile guidance, whereas you can talk about other systems as well. We have actually experimented some of these concepts of IGC and things like that in UAVs and all that. Yeah, but here the primary focus will be on missiles actually. So, when you talk about missile guidance and control, you also need some information about target actually. So, that target information is typically captured either through radar or seeker. So, we have some sort of a target estimation loop, and this target estimation loop also talks about missile guidance, position and things like that, position and velocity vector. So, that the relative error between them, this target and missile kind of gets estimated and all that actually, and that is what it is fed to the guidance. Guidance gives some lateral command and things like that, which eventually goes to the control. Control can have its own loops, which are not putting in this block diagram. It can have 2-3 loops by itself, then it will finally go to actuator. Actuator will give some command of fin deflection, and fin deflection is something that couples with the missile aerodynamics, and hence its orientation changes, its force moment changes, and then it corrects its path actually. So, this is all what it happens. Okay. So, when somebody talks about estimation, he typically ignores all the things inside this guidance, control, like actuator, all that. When somebody talks about guidance, he ignores everything else, control similarly, things like that actually. So, now the question is, can the time lag between various loops be reduced? Because the moment you talk about loops after loops after loop, what happens is inner loop should be sufficiently faster than the outer loop. In other words, outer loop has to be sufficiently slower than the inner loop. So, purposefully, if this one has some actuator bandwidth and all that, this control design what you are talking about has to be slower than that, guidance has to be even slower than that, and estimator has to be even further slower than that actually, in error closing sense basically, that is it. Okay. So, the question here is, can we really not do some guidance and control together? Because if you see this, the guidance is typically done based on point mass or kinematics level to some extent, whereas control design is typically done using this 6-DOF equations of motion actually. Now, the question is, if 6-DOF equation of motion is used in control design in any case, then 6-DOF contains the position and velocity information also basically. So, why using a separate dynamics for guidance and then invoking some approximate dynamics and all that actually. So, that is probably not needed. That whole idea, if you try, people have thought about and then try to combine these two loops, and then concepts of something called integrated guidance and control starts appearing. Then some people think about, well, we can also do this way, we can combine estimator and guidance, because guidance essentially talks about target information all the time. So, estimation and guidance, why talking separately? We can talk together. So, that leads to this integrated estimation and guidance. And some people talk about everything together. I mean, this estimation, guidance, control at different level, fusing them together, and that leads to this IEGC concept, integrated estimation, guidance and control. So, this IEG and IEGC we will see that in the subsequent lecture, but today we will talk about this fusion IEGC, integrated guidance control, and especially we will talk method that we have proposed recently, called what we are calling as partial integrated guidance and control. So, alright, so this is the topic of discussion today primarily, because if you are interested in talking about or learning about various things on IGC, there are several literatures available. Obviously, it is not possible for me to discuss many of the concepts that has appeared. If you are interested, you can read yourself. But one of the concepts that has emanated from our own lab, that is what we call as partial integrated guidance and control. That is what I am going to talk in this lecture actually. The primary references of this are several conference papers that appeared in 2009 and interestingly appeared in sequentially May, June, July and August 2009 at various levels of various techniques and various issues at trust and things like that. And if you really are interested, I suggest that you can read some of these literatures for more detailed explanation and all that. We are also in the process of writing some journal paper and all, but so far it has not appeared anywhere actually. Alright, so outline of the talk is something, the subsequent part of this lecture is something like this. We give a very brief overview of conventional guidance and control, followed by philosophy of IGC design, its merits and drawback at the philosophy level. We will not go details inside actually. Then we will switch over to this partial IGC concepts, and then we will take a typical real life example of endo-atmospheric interceptors engaging against ballistic missiles, incoming ballistic missiles, and we are assuming that the ballistic missiles can take ballistic trajectory only. They cannot go through this typical the spiral motions and things like that. Okay. But still, we assume that the target is some sort of a ballistic re-entry vehicle with very high speed, and then we have some sort of endo-atmospheric interceptor where we want to intercept it before it comes ground actually. So, that is the type of problem. Then we will follow with some numerical results. First is nominal case, and we will also give some comparison with conventional design as well as IGC design actually, and we will demonstrate that this partial IGC happens to be in some sense better than both actually. Okay. Then we will address some of these practical difficulty issues, information availability, then zero effort misbehavior, perturbations with respect to initial condition, computational time issue, implementation with seeker noise, robustness with respect to parameter inaccuracy. All these things happens to be very practical issues, and unless all these things are addressed sufficiently, it is not really a very good design. So, we will see some of these behaviors with respect to this. Then we will have some concluding statements actually. Alright, so very quickly, what is motivation and philosophy of partial IGC? This is a typical guidance scenario, and some of these are very clear from the guidance lecture as well. So, we have a missile and we have a target going its own way, and missile is chasing that probably. And then this missile, if you continue to go in this direction, it may miss the missile, it may miss the target. So, what happens is there will be some sort of a direction correction, and direction correction happens in such a way that the LOS vector does not rotate actually. It's a typical 2D picture. And so, ultimately the LOS vector does not rotate, and finally it leads to this collision triangle sort of thing. There will be slight path correction sort of thing here actually. Okay, so that finally this vector gets in a slightly different direction sort of thing, depending on what target does. And that is done typically through lift generation, and lift by mass is typically what is lateral acceleration, so AM. And AM, when you apply this lateral acceleration, this velocity vector gets a turning, and this is what it happens. So, how this AM is generated typically is done through this very simple looking guidance laws, which is NVM lambda dot proportional navigation, and there are several variations of that. Okay, there are something like true proportional navigation, pure proportional navigation, then augmented proportional navigation, modified proportional navigation, things like that. Various things are available. But the fundamental philosophy is like that. If either AM is perpendicular to VM or AM is perpendicular to this LOS. Okay. Then if it is perpendicular to LOS, then it is something like VC. If it is perpendicular to velocity vector, it is VM. And there are again discussions in the literature which one is better than over, depending on the situation actually. Anyway, so this is a summary of this in a very conventional sense, but there are several issues there. But once you generate this AM and if you extend that to 3D, then one will be in the z direction and the other one will be the y direction sort of thing actually. And remember, in the x direction, in the velocity vector direction, typically you don't have a control action basically. So we have to live with that, and that the engagement is assured typically based on the time to go information actually. Okay. Anyway, so this is what it is. So once you generate this lateral acceleration, this is the guidance command generation part of it. Then there is one more loop which will take this guidance command and then convert it to equivalent body rate command actually. So that is what body rate command generation will happen. Then you go to the inner loop and it will look, I will take this rotational dynamics, in other words P dot Q dot R dot equations and all that. And then I will use those equations to generate this delta, delta P, delta Y, delta roll, pitch and yaw basically. Then it will be fed to through the actuator dynamics, and then finally it will be fed to the missile dynamics, and then the vehicle gets course correction basically. So what are the things here? First of all, it kind of exploits the inherent timescale separation property. That's the very good part of it, because when we talk about guidance, we really don't worry so much about the body attitude actually. Okay, the orientation of the body doesn't matter. Ultimately, what matters is taking the vehicle from point A to point B. So in a point mass sense, that's the guidance problem. In other words, very precisely, the guidance has to translate the CG of the vehicle to a desired location wherever target is actually. Okay, so that's that kind of thing. So we typically separate it out, the body rate part and things like that. What happens is body rates is typically fast dynamics, whereas velocity vector level, that u dot v dot w dot, that component level, or even point mass dynamics level, the equations are slow actually. Okay, in other words, takes some time to evolve actually. So this timescale separation property between faster and slower dynamics are typically retained here, which is very nice, and that is why the tuning difficulties are typically not there and all that actually. So easy mechanization with easy tuning also, relatively easy tuning, I will say that way. And but the drawback is overall design is non-optimal, even if the subsystem becomes optimal. And also this limited coupling, because of this point mass here, 6 stop here and things like that, because of this limited coupling, it typically leads to large number of design iterations as well. Okay. So this is the good part is it exploits the timescale separation property, and hence it gives a certain advantage, including easy mechanization, and but it has this drawbacks actually. So to address these drawbacks, let us understand what is going on here. So we have this outer loop, okay, whatever we are talking about, the outermost loop here, guidance generation part of it. Then there is a body rate generation. In other words, this is, let's say, 1 can be assumed as guidance loop. And this intermediate loop has to track this command. So that means 2 has to track this one. So that is how it is. And 3 has to track 2. So that 3 has to be, 3 has to go and merge with 2 basically. So that is how ultimately 3 goes to this reference command dotted line actually finally. Okay. So that is how you can think of understanding basically. But what happens here? Just some observations before we move on. This many classical missile guidance laws are typically inspired from nature. And especially proportional navigation is inspired from the so-called collision triangle conception and things like that, typically geometrical behavior. Then control theory based guidance laws are also there, but they typically take either kinematics or maximum some sort of a linearized dynamics and things like that. So essentially they are not very effective also. So in my own view, and so which is typically all modern theory based, modern control theory, and especially this nonlinear optimal control theory based on guidance laws are typically is a natural tool to obtain very effective missile guidance laws. The only constraint is probably this computational difficulty that bugged people for a long time. Can it be overcome actually? What about autopilot design part? Again, autopilot design parts are also based on typical classical control theory like root locus, body plot, PID control, lead lag compensator, things like that. And typically these are based on linearized seesaw model, single input, single output model. So essentially it takes a lot of effort and tuning to make it work. Okay. So linear modern control theory based MIMO techniques are available and they are slowly gaining popularity as well. However, nonlinear control design approaches are also evolving and they are typically not that much used because of lack of good robustness evaluation tools. They may have, they may have robustness, but evaluation sense the tools are not there, hence the confidence level is not there to go there actually. Okay. But having said that, there are certain cases where people have actually ventured out and then implemented nonlinear control design also for the autopilot in real test flights actually. Okay. And then sometimes these nonlinear designs can be unnecessarily over conservative also. For example, the nonlinear H infinity control if you want to use, sometimes it may be too sluggish also. That is another reason why it is not that popular. Having said that, if you address some of the concerns, then obviously the design can be very, very powerful actually. So, what is essentially the drawback of this conventional 3-loop guidance and control synthesis? First of all, there is not too much of synergy between guidance and control. And in essentially the guidance either completely ignores the vehicle dynamics or only accounts for a limited point mass dynamics. Okay. So, the dynamics happens at 6 stop level, that too I mean assuming rigid body and things like that. Typically 6 stop is capable of capturing many things that goes on into the vehicle dynamics, but the guidance completely ignores that or very limited sense in point mass sense only it will talk about that actually. Okay. Then it essentially leads to large overall loop delay, and essentially this is not very good in time critical applications. That is that's my strong view actually. That means when time to go T-go is small, then you don't have a luxury of having this long settling time actually. Okay, so that will demonstrate in the next slide probably. So, sometimes the nonlinear designs can become unnecessarily over conservative, that I already talked, but anyway. So, the point is that it may result in large overall loop delay actually. Okay. And that is when T-go is small, it is not acceptable. Okay. So, overall design approach is typically non-optimal and hence it requires a good amount of effort. That means it really requires a good amount of tuning effort to make it work near optimal. I mean, you can talk optimal, but if you really want to work it near optimal, then you essentially need lot of tuning effort actually. So, for this fact, people have thought about putting them everything together, IGC sense, and then tell, okay, what about just one loop? Because every information is contained, target information we have, initial information we have. So, simply just do some math and then generate this spin deflection directly basically. So, essentially it leads to this line of thought that it results in some big advantage, essentially synergy between guidance and control, optimal performance of the overall system, because there is nothing called point mass equation anymore, everything happens at 6 stop level, and there is essentially no lag between guidance and autopilot loop, and hence we assume, I mean we expect some improvement in the missed distance as well. Okay. But what happens here I mean, so advantage wise it is synergy between guidance and control and optimal performance, yes. What is the drawback? Drawback is in our own observation it works, but it works only with small perturbation about collision triangle. Otherwise the tuning becomes quite difficult actually. So, design tuning is difficult because of the conflict in problem objective and control effectiveness. Okay. Problem objective is to translate the CG from point A to point B, which happens to be the target position. Whereas, the control effectiveness happens in the rotational dynamics, because what happens typically is if you deflect a control surface, it is not there is a small delta force generation, but force generation is not important. What is important is moment generation. Because of this delta F, there is a long momentum, and then long momentum results in lot of moment, and hence the body gets rotated actually, which is typically ignored in the point mass level. Body orientation is ignored. So, any amount of controls, I mean any amount of control surface deflection has to account this body rates explicitly actually. If it does not, then it leads to a lot of tuning difficulties, because what happens is this delta P, delta Q, delta R or delta R, delta P, delta Y, they also appear in the velocity level equation u dot v dot w dot or v dot alpha dot beta dot either way. So, if your objective is to translate the vehicle from point A to point B, then implicitly in the design process, these fins and deflections get generated through the velocity level equations, which are not good actually. We have to go through the moment level equation, then the tuning will become very easy actually. So, this is what is written here. Control attempts to alter the translational dynamics directly rather than through the rotational dynamics. That is the whole observation there. So, this causes the rotational dynamics to overcorrect, and hence the vehicle becomes unstable. If you are not very careful about this fin deflection sort of thing, because what you are doing is typically it generates the fin deflection from a relatively lesser powerful component, and then the deflection becomes more, and if it becomes more, then the rotational level its effectiveness is very high, so it will rotate the vehicle further, and then it will go to instability and all that actually. Okay, so those are the drawbacks. So the motivation for partial IGC is like this. In other words, we want to retain the benefits of the IGC, but we want to overcome the drawback of it actually. Okay. So the questions are like this: can the inherent timescale separation property between translation and rotational dynamics be preserved and exploited? We want to keep this property and exploit that as well. But the problem, the conflict between problem objective and control effectiveness has to be avoided. Okay. In other words, the guidance correction must happen through the rotation of the vehicle and not through the translation actually. So the point here is the control authority is more effective in rotational dynamics than the translational dynamics, and hence that's the requirement actually. So let's understand this concept again. So we have this guidance followed by body rate generation followed by fin deflection. So guidance takes a long time, and let's say settling time of the guidance loop is typically here. So problem objective is done somewhere here. In other words, if your time availability is more than Ts, then probably this missed distance is very small. That's not a problem so much actually. But what happens is we don't want to look at those problems. We want to look at those problems where TGO is very small, especially when the incoming ballistic missiles comes with a very high speed. Even though separation distance is let's say 30 km, when seeker opens up and sees the target, the 30 km distance is typically covered in 3, 4, 5 seconds actually. So that becomes a small TGO problem really. So then in those cases, what happens here is we want to do something so that this outer loop is avoided. Okay. So remember this innermost loop is capable of following the second loop, but by design the second loop has become quite slower because it has to track the guidance loop. That's the whole idea there. Now let's get out of this loop 1 or the guidance loop, then directly talk about body rate generation. Can we do that? If you do that, probably this body rate generation can try to catch up this commanded value very fast, and hence this 3 will also catch up with that. Now that is what is reflected here. So instead of having this kind of a picture, we will have something like this kind of a picture. Okay. So essentially what has happened is initially our settling time was somewhere here, but by doing this we have been able to kind of reduce the settling time that much actually. Okay. So that means even if let's say the some small TGO problem, the real TGO happens to be somewhere here, okay, then also we will be able to do it because our settling time has reduced here, and our TGO is more than settling time now. So we will be able to do the job actually. So the idea is like this. So we have this guidance, body rate, fin deflection and all. What we are telling here is come out of the typical guidance loop, and whatever is left out is what we are calling as partial IGC design actually. So it exploits the inherent timescale separation property, and then it operates essentially in 2 loop, not in really 1 loop, but we want to operate it in 2 loops actually. And so the commanded body rates are generated in the outer loop, okay, directly, and then using those commanded body rates we generate the fin deflections in the inner loop. That's the whole idea here. So advantages, again just to summarize, it's a new philosophy altogether and tries to kind of combine the advantage of IGC and conventional design both. Very minimal tuning requirement, and that's a big fact actually in my view. If you happen to see the IGC community and things like that, happen to talk to them, most of the time most of the designs have this tuning difficulty actually, but in PIGC we really don't have this tuning difficulty actually. So very less computational time, because that is something that we cannot avoid, and it has to have, otherwise all these nice concepts are useless. So what we are doing here is outer loop we are proposing this MPSP or MPSC, that what we have discussed before, these 2 techniques, and then inner loop we are trying to use this dynamic inversion concept. So this is a nonlinear control design approach. Okay, so successfully verified for a large number of initial conditions for both interceptor and target as well, and comparison between conventional 3 loop and SDRE based 1 loop design is also there actually. So essentially the conclusion turns out that partial IGC happens to be better than both, but instead of simply telling in English words, we will also go through some of the results and then see why it is happening. Again, these are the concept that is available in some of these references. You can find more details on that actually. So implementation of this partial IGC is typically done this way. Remember, body rate generation okay, either MPSP or MPSC, whatever we are talking about. Okay, then this one will have this Q star and R star available actually. Okay. So, this Q star R star generation mechanism will give us this desired body rates Q star and R star basically. Okay. And then what happens, okay, to tell the little more story actually here, see whatever TGO we get from this PN law and things like that, initial guess, essentially the whole idea here is to nullify the errors in the two channel to two axes and then stick to that that zero error actually. So, very quickly, I mean we will have this okay. In other words, if your TGO is somewhere like this, your estimate can be somewhere here, but the real TGO can be very close to that. Okay. So, during this period, whatever period is left out, we can think of implementing some DI based guidance thing there, and that is why it is written MPSP, DI and all that. Up to here it is MPSP. Any small time that is left over, that means error has gone to 0 in two components, it needs to remain at 0 for the remaining time. Okay. So, the remaining part is typically done through DI. Details actually you can see that in the paper actually. Anyway, so that is that part of it actually. Okay. So, but also remember we need to stabilize the roll rate, because without roll rate stabilization things can go very bad, because seekers cannot see the target. Pin deflections, resolution. In other words, what you are generating is delta, delta P, delta Y, but ultimately any missiles have actually 4 deflections, 4 pins, delta 1, 2, 3, 4. So, there is some pin deflection logic where you generate this delta 1 to 4 using these things and then recombine back and things like that. So, the details I am not showing here, but this can be done in a good way provided the body rate is stabilized. That means, no further body rate is there, or its body rate is very small. In that sense, it can be done. But typically, roll rate is also a sensitive channel, because your IXX, the moment of inertia IXX is very small, and the moment that gets generated is large actually. Okay. So, your P dot becomes non-zero and it doubles very quickly. So, that means your body will start rotating violently and things like that actually. In those situations, even though guidance is good and all, nothing can be done actually. So, we really need a stabilized roll rate to do anything like guidance and all that actually. So, that part is assured by assuming this some zeta variable, where zeta dot is assumed to be P, and then this variable is paired so that P dot can be computed, and then P star can be computed, and P star, Q star, R star are now available in this loop actually. So, this P star, Q star, R star can be utilized and then directly you can get the pin deflection and then operate it actually that way. And remember, the entire this body rate command generation can be thought about like as outer loop guidance sense. So, everywhere the full information is required, that all the variable that goes into the system equation has to be fed back actually, and this Q1, Q2, Q3, Q4 are typically quaternion components actually. Other applications as well, we have done collision avoidance of UAVs and then you can also implement it for formation flying of UAVs. So, similar concepts, different techniques and things like that. You can see some of this literature again if you are interested in more about the concept of partial IGC. The way it is implemented for this missile problem is different from these things, but still the concept remains very similar actually. Okay. And typically these are dynamic inversion based, here also basically. There is nothing called MPSP, MPSC and all that way. Anyway, coming back to this particular problem, this partial IGC design for endoatmospheric interceptor for ballistic targets especially. So, let us see to move a little more on to that. So, there is a threat missile which is launched somewhere and all that. This picture is taken from internet, I do not know the website I have forgotten, but then typically taken from internet. So, this is a threat missile which is launched towards the target somewhere, but so this is the defending region basically. So, this is where typically the defending missile has to be launched, and before it intercepts, before this threat missile comes down, it has to be intercepted way above ground actually. And if such a logic operates for this class of vehicle, then it can also engage with the conventional targets like aircraft and things like that way. So, this is the whole idea of typical engagement scenario. Informations are given based on radar, and then this vehicle itself will have a seeker towards the end and things like that. What we are talking is the very last segment of from here to here for the interceptor, and probably some here to here for the target actually, so that kind of thing. So, the challenges here is first of all very high speed targets, that means very less engagement time, the time availability is very short, And also remember very high line of sight rate. I mean, that's the fundamental thing for any guidance, no matter what technique you use actually. If your line of sight rate changes, I mean, you have to really react yourself very fast also basically. So, if your line of sight rate is high because the vehicle is let us say going in some sort of a cross plane sense if you are engaging. Okay, remember this picture if you see, if it is going in some plane and you are engaging in some other plane actually. Okay. So, if that kind of a situation happens, then anything that comes in a very high speed here, okay, it reflects in large LOS rates actually. Okay, and that generates a lot of difficulties. Ultimately, we want zero miss distance or very close to zero miss distance, because these incoming targets are also having very good shielding for their own weapon system and things like that. So, unless there is a direct hit or very close to there and the very good impact of that, nothing happens there actually. So, we have to go there and then have this zero miss distance finally basically. Okay. So, that is why this PN loss and all are not very effective, because one line there is a singularity towards end actually. So, that becomes a major issue there. And then there is a constraint of impact angle and aspect angle, things like that. So, that also has to be accounted for. Not only the engagement has to happen in a zero miss distance sense, but it has to happen in a particular angle sense actually. So, that can happen. And the drawback is we have this lateral acceleration saturation, because the dynamic pressure is less as you climb up and up and up. Okay. Once you have dynamic pressure level, once the dynamic pressure level drops down, obviously this engagement has to happen in a, the difficulty comes of turning the vehicle actually. That's the whole idea. Alright, so a little bit math here. So, this is the target, has its own axis and system and all. This is your line of sight. This is the vehicle or interceptor, missile, whatever we call. It goes to engage the target actually. So, it has its own axis system, but this entire formulation, any guidance problem has an inertial axis frame also, where you see the engagement actually. Okay. So, the vehicle has its own body axis system. It has an inertial axis frame. And then what you are telling is the entire equation of motion is given in the fin frame, which is typically rotated by 45 degrees about its own body axis actually. And that fin frame, we are imagining one more fin frame sort of thing, is located at the inertial frame center. That is just a mathematical formulation of the problem actually. Okay. So, this is what you see, inertially located fin frame actually. Okay, that is what you are calling here. Okay, the orientation keeps changing, but the position does not change for this frame, but this one, the both position and orientation keeps changing actually. Now, the equations of motions are given like that, no approximations involved in anywhere, it is the complete full 6-stop model. So, you have this u dot, v dot, w dot, p dot, q dot, r dot dynamic level equations. So, these are quaternion components, these are the gravity terms, all these g term where you see here, these are disturbance terms, okay, which are typically to some extent these are known. So, there will be some degree of unknown quantities as well for that. And then if you go back to this kinematic level, you have this quaternion components, and then we are not talking about position of the vehicle itself, but relative position between the vehicle and the target. And this relative position is seen in this rotating fin frame actually. Okay. And when you have derivatives taken in a rotating frame, then this omega cross r term has to be accounted for, and doing all that, we will end up with something like this equation actually. So, these equations, what you have 6 equations here, 4 here and 3 here. So, 13 equations total, but we will also have a quaternion constraint equation, which is like q1 square plus q2 square plus q3 square plus q4 square is equal to 1. Okay. So, that algebraic constraint will also act on it. So, that is where the complete 6-stop equation is given for this vehicle. More on this rotating fin frame concept one can see by going to this reference actually. Okay. Alright, so the target model is typically a point mass model, because no sensors are available as of now which can give the 6-stop level detailed clarity of target dynamics, which obviously is impossible to do as far as current technology concerned. But we can certainly get the information at the point mass level, and typically that becomes sufficient actually. Okay. So, this point mass level equations, you have 3 dynamic component and 3 kinematic component. Remember, everything happens in 3D actually, And also there are some assumptions about the target dynamics. First of all, we assume endo-atmospheric engagement. We assume ballistic entry, that means no lift, only drag is there. Then we have this gravity turn is accounted for, okay. And then no intentional end or spiraling maneuvers actually, no intentional or unintentional either way, okay. So sometimes this spiraling maneuvers are unintentional also, because of the physics of the problem it happens that way. But that's the reality, I agree with that. But this particular experiment, we are proposing a new concept altogether. So we thought, okay, we'll propose it with respect to non-spiraling targets, but it has its drag actually, which is a major component, okay. So that is how it is defined actually, okay. Anyway, so the philosophy of this time scale separated partial IGC is something like this. We have already talked about that. And then advantages, we've already talked about that many things, but the outer loop, we are using this MPSP or MPSC, both the candidates, and both the things we have discussed in detail in one of the previous lectures actually, both the techniques, okay. So advantages of using this technique in the outer loop, turns out that it actually has a hard constant formulation. That means one of the things that we are looking for, zero mesh distance, is we can aim for now, because we have a technique which can do that. We have minimum control effort kind of formulation here. It also has the closed form control update, so computational time is less, and essentially it can be implemented online. That's what we strongly think actually, okay. So compared to these two, MPSC, SP and MPSC, then this particular thing, MPSC has a little more advantage, that control smoothness is guaranteed by formulation and computationally slightly more efficient than MPSP actually. So that's what it is, okay. So then outer loop design, we have taken all these things, UV, W, P, remember Q and R are control variables here. So P happens to be a time varying parameter sort of thing. So these are the states that are considered in the outer loop, and these are the control that is assumed in the outer loop actually, okay. So the output vector turns out to be like this. Remember this is in the framework of this particular design. Now you need the state dynamics, you need output vector which has to go to some desired output values and all that at t goes to Tf. So these outputs are typically, this is what it is. You have to have this YRM and ZRM, relative dynamics in the inertially located fin frame in the y and z direction, they have to go to 0, and relative velocity in the y and z directions would also go to 0. That's the formulation actually, okay. So these techniques also require some sort of a guess history. So we thought of implementing a PN based 3-loop design and then took the guess history from there. So this design, we talked about that before. We have a linear parameterization and then this constant equation. Detailed math is already discussed, so I don't have to talk about it here. But essentially, it is operating based on the same technique actually. Okay, so these are the desired vectors 0, 0, 0, 0. This is the actual vehicle parameter. This is the desired vehicle parameter when t goes to Tf actually. And we implemented everything with respect to a 3-loop design based on this modified PN law followed by dynamic inversion control synthesis and all that. And that gives us a kind of a guess history to start with, and also gives us a platform to compare our results with respect to those results actually, okay. Then coming to the inner loop control, we have this fin deflections and inner loop outputs or something like this, and the formulation wise y should goes to y star in the dynamic inversion sense. So we define this error and then enforce this error dynamics, okay, where k is a diagonal matrix with the diagonal entries being this 1 over tau sort of thing actually. And settling time, remember how small you have assumed. Settling time you have assumed as 0.4 seconds. Okay, so less than half a second we want the settling time to happen in the inner loop actually. Yeah. So the outer loop can close in something like 3-4 times of that. So around 1.5-2 seconds time, we expect that things will be the error will go. So any time to go which is more than 2 seconds, probably we will be able to handle actually. Okay, so that is the whole idea here. Alright, the control update equation is in closed form. Those of you who don't know dynamic inversion, I encourage to see one of my lectures in the previous, another parallel course on advanced control in this NPTEL program. And then you can see why this dynamics are coming like this actually. So details also you can see in the papers actually that way. Some simulation results, this is what it is. We have this the target coming in, see ballistic targets typically come in a straight line sense because there is no maneuver there. but the speed at various locations are different because drag is there actually. Okay. So, typically this is target is coming and missile is going and engaging here. So, you can picture really the zero miss distance actually. Okay. Okay. But we will see the values also basically that way. Okay. Anyways, the roll rate and all you can see very soon they are stabilizing. Okay. Whatever initial condition so remember the roll rate has to go to 0. That's what the roll rate stabilization has to happen. It is happening. And whereas the pitch and yaw rates are typically generated from the guidance loop, that need not go to 0 because you really need to turn the vehicle to go towards the target actually. So, this is what the final solution is. Okay. This is the desired pitch rate and this is the desired yaw rate. Okay. Interestingly, it happened to be kind of straight line actually, very close to, you can see these are straight line actually. Even if it is implemented in MPSP for a framework, where you are not really enforcing any straight line equation basically. Okay. But anyway, so they can see that very quickly the inner loop tracks the desired dynamics and hence everything happens in a nice way. Remember, settling time is 0.4 seconds, that is what you have assumed here. Okay, so 0.4 seconds somewhere here actually, so it is happening there. Then fin deflection sense also you can see they are very smooth, they do not have this singularity issues and things like that. And also the bounds are typically plus minus 5 degrees, which is very less. And typically the bounds will be something like 20-30 degrees reflection, but whereas you are utilizing only about plus minus 5 degrees actually. In other words, the scaling becomes in from T0 to TF in such a way that the demand does not become very high towards the end, which typically happens in a conventional design sense. You can see this is also comparison between this conventional and typical, the partial IGC that we are proposing. So, this is roll rate is not too much of a difference, but if you see pitch and yaw rate, that is where the guidance loop closes in. You can see some saturation here, okay, and more important towards end actually, that is what will reflect in miss distance actually. Because here we are purposefully bounded it to the 20 degree per second limit. And that is why it is stabilized there actually. Okay, we are not allowing it. If you allow it, it will go a lot higher than that actually. Okay, so that is avoided completely in this new formulation. And engagement with different initial condition, we have tried out for several cases. Once you tune it, just forget it. You just keep on changing the initial condition, run your program actually. So that is what is done here. You can see various initial conditions for the missiles, various initial conditions for the target also, both in position as well as distance. No matter what it is able to engage the target actually. Okay. And this was a little frustration. If we have actually implemented one IGC concept based on SDRE and tried several things for a couple of months altogether, but no matter whatever we did, the final disappointing news is something like this. If the initial error without doing anything happens to be around 55 meter, we are able to correct only up to 39-40 meters actually. So, there is not too much of a gain that way. But again, this SDRE technique is a little bit funny technique. It depends on SDC and things like that. So, we do not claim too much into that. What we claim is to the best of our ability and tuning, this is what the results that we got. And typically, if the design methodology is good, then it should not be based on designer's experience and things like that. So, that is what a good method will demand actually, will result in that basically. So, without claiming claiming too much, what we claim is in our best effort, if the miss distance is initial zero effort means without doing anything happens to be the order of 50-60 meters, then some correction may happen, but this is nowhere close to what we really want actually. Okay. So, this in our experience, this one loop IGC was a complete failure actually in some sense. You can see the numbers here, see this conventional designs, if you have this zero effort miss without any corrections, if it happens to be the order of 500-600 kilometers like that, 600 meters like that, half a kilometer, then no matter whether you implement this conventional IGC, conventional guidance and control 3 loop design, then also relative miss distance is very low. If you use our time scale separated partial IGC, this is also very low. Okay, but if you compare them very closely, these are lower than these values actually. Okay. Whereas compared to the one loop IGC, these are 50 meters, 40 meters like that, then only it works. If initial conditions are such that the initial zero effort miss is of the order of this high, half a kilometer like that, it does not work. It does not, correct the error at all actually. Anyway, so coming back to this is the, if this happens at least, then there is some correction. 55 become 39, 53 become 32, 27 becomes 11 like that. but nowhere close to what this is less than 1 meter level accuracy, what you get it here actually. Okay. So, that is the more important part of it. These are again comparison between conventional PIGC designs in terms of fin deflection sense. And see the momentary deflections here are quite large, whereas the red line is smooth and small everywhere actually. Okay. So, essentially no chattering and no saturation, and hence we can think it has higher capability and all that actually. Now, coming to some real quick practical issues, as I told in the beginning, there are issues something like information availability. Receiving so much information feedback, are they available or not? Then there are ZDM behavior, zero effort misbehavior, finally what happens there? Then perturbation in initial conditions, computational time issue, implementation with seeker noise, and robustness with parameter inaccuracy. So, these questions are like that. Again, it is kind of put it in a question framework sort of thing. So, the information availability issue sense, what you are thinking is, okay, all these things are required for implementing actually. Okay. Now, the good thing is this UVW and quaternion components as well as position, these are all available from the INS system. And INS system is typically very good. I mean, you do not really need a filter in the loop also you can blindly rely on this information actually. Now, we also need these information, target position and target velocity vector direction and all that. That is typically available through some sort of a seeker information. But also remember, anytime what we want this information, we have to also utilize some sort of a filter design, and typically that is done through Kalman filtering. So, that part we are not talking here. So, remember we are fusing guidance and control, we are not touching the estimation loop. So, but typically these informations are also used in whatever best possible way you are using for the conventional design. Probably same thing can be thought about to extract this information and then couple with that actually. What about ZDM behavior? Okay, if you see the conventional loop, it is very lot of chattering here initially at least. I mean, this is the real reason why you require lot of battery power consumption and things like that actually. Okay, your delta dot requirements will reflect in all sort of things. But anyway, so we will not go too much detail into that. What happens here is, if you deflect the fin deflection and do not do anything for the rest of the time, then you have some station, and that one you keep collecting and then plot actually. Okay. If it happens to be smooth, then the design is much better actually, and you can see compared to the blue line how better is the red line actually. Okay. Alright, now what to do with the robustness part of it? There are some issues like sensitivity with respect to the modeling or parameter inaccuracy, things like that. So, for that part, we propose that you can incorporate this neuroadaptive design in the inner loop only basically. Okay, so that means this rotational dynamics where you generate the fin deflection, if that is done properly, then everything else will be taken care, and that is typically done through this neuroadaptive design. And what is the philosophy there? We have this P dot Q dot R dot or this YD dot sort of thing. This is the desired dynamics actually, and this dynamics can be thought about without any perturbation, without any accuracy issues and all that. But the actual output dynamics is different. It has this disturbance term. In other words, this gets generated from this parameter inaccuracy and things like that, and it happens to be a kind of a critical issue for any aerodynamically controlled vehicle. Because aerodynamic is some part of it will always be kind of tabulated data, okay, and the confidence level will be fairly good, but you expect some 10-20% error all the time actually. Okay. So, that is the part which will result in this dy, and also if you have some neglected dynamics and things like that, it also appears in the form like this. So, the concept here is, okay, we know these two. So, the idea is, can we do something so that y will go to yd very quickly actually. Okay. So, this is cannot be done directly because this part is not known. So, the whole idea is, can we know it first, and that knowing part is typically done, okay, through some neural network approximation. So, whatever you do not know here, that one is we attempt to do that using a neural network actually. And once you do that, and there is some sort of additional term for making it a kind of a completely observer dynamic sort of thing actually. So, then this term helps us in having the smaller bounds and things like that also basically. And those of you are interested, you can see this 2009 GNC paper, the AAA GNC paper, then you can see more than that actually. The whole idea is once you put it here, this term is an approximation to the neural network and this additional term is there. This is not same as anything like this, but our objective lies here. So, typically it is done in two ways, that y should go to ya and ya should go to yd, that is the design. Whereas the objective lies that y should go to yd basically. So, what we do is we force y to go to ya and then ya go to yd. And then ya to yd is done directly, okay, that part, but y to ya is typically done through this Lyapunov design and things like that actually. Okay. Details I will not say, okay, it will excite different branch of mathematics altogether using Lyapunov theory and things like that. But having said that, this is the engagement scenario with adaptive design with parameter inaccuracy of the vehicle sitting there as part of the modeling actually. Now, you can see the difference here, and this is there are three plots here. One is actual with nominal control. Okay, this is the one what you see nominal. So, first is nominal control applied to the nominal plant. So, this is the thick blue line what you see here. But if you don't do anything, don't do any adaptation and things like that, then you will operate simply based on feedback. That means your feedback formula will be same, but your states will be coming from the actual state and things like that actually. But even then, see the deviation actually. The requirement is somewhere there, but the actual happens to be far away from there, and that is here also, here it also. And because of that, there will be a heavy amount of penalty for the misdistance. However, if you put the adaptive control back into action, then what happens is this red line what you see here, okay, it actually very close to the thick blue line. That means you will feel as if nothing has happened actually. Subject to the issue that okay, this D is approximated very quickly actually. Now, these are the perturbations that we have discussed. I mean, these are the parameters that are affecting the vehicle dynamics greatly. So, we have taken some nominal and then some minimum maximum value sense and things like that. And then you can see that okay, if the nominal design is degraded, that earlier remember it was all sub-meter level accuracy, okay, within 1 meter and all that. Now, if you have parameter inaccuracy like that, then the same thing will result in higher misdistance, 30 meter, 40 meter like that actually. But if you put the adaptive control back into action, then it is again come back within 1-2 meters actually, okay, maximum 2.83 meters like that actually. Okay. So, you can see the number difference and you can claim that very easily. You can see that there is a substantial enhancement of robustness actually, okay, in the misdistance sense directly. It is not that the vehicle is getting fragmented or its roll rate is very high, it has gone unstable and things like that. Even though it may operate in a little bit stable manner, it is going somewhere else, not towards the target. That is the whole difficulty actually. And we cannot afford to have 10 meter, 30 meter, 40 meter misdistance. This problem does not allow that actually. We remember we have to have 0 misdistance or something which is very close to 0 actually. And also remember when somebody calls 0 misdistance, not physically 0, it is between the suppose the relative radius of the target and the radius of the missile. If you take them together, any number that comes below than that can be considered as 0 misdistance, because it's then it will result in physical hit actually. Okay. So, anything that is typically less than 1 meter, 2 meter probably, depending on again target and missile radius and all that. So, we can think about it as a 0 misdistance less than 1 meter, but within 1 to 2 meter or 1 to 3 meter, we can think around that figure, we can think about something like near 0 misdistance. So, that is what is happening here after we put the adaptive control back actually. Okay. Now, there is another issue that bugs us is how to deal with the seeker noise, because ultimately no matter what what Kalman filter, EK, UK, whatever you put, there will be some sort of residual error actually. It is not never filter out, any filter does not filter out the noise totally basically. So, there will be some degree of inaccuracy in the output of the filter, and remember these are all predictive logics, MPSP, MPSC and all that actually. So, any amount of velocity direction error sitting there will result in a lot of repercussions actually, because if you are aiming, okay, let me pictorially show that there is a target here, your estimation tells there is something here, but if you have a small error in the angle there, then it may come out to be something there. So, your vehicle will typically go towards that, whereas the real target is somewhere here. Okay. So, that is the difficulty. If the real target is somewhere here, okay, where your guidance should be actually taking towards that, not towards the other one actually. Okay. But as far as information content is there, it is telling that okay, it is going towards that direction. So, obviously, missile gets misguided actually in a way. Okay. So, how to handle that issue that way. So, then the idea here is we have what you are telling is okay, prediction of the target trajectory is done with seeker output averaging over a finite window actually. I'll demonstrate that in a picture actually. You take up a little bit finite window and then kind of do some sort of averaging of whatever value you are getting over a period of time and then slide that period and then keep operating based on that actually. Okay. Also remember that towards the very end seeker data becomes very highly noisy and things like that because of several other issues like glint noise and other things there. We don't talk about that. Towards very end, less than 1 second to go and things like that. We really don't have to account for that. We simply we propose that we can go based on only prediction mode actually, which is still debatable in a way. How far you can tolerate, how less you can tolerate. That becomes still a kind of topic of research actually. Okay. Anyway, coming back to that, this is what is done. So finally, remember 25 millisecond is what you have assumed for the seeker update data. So what you are telling is first 5 data will simply observe, will not react, the guidance correction will not happen. We will simply observe what the target is doing, which direction it is going. And when this guidance loop closure happens TG, we already have at least some finite window data sampling actually, some 4-5 data or depending on what level of mechanization you want to do actually. Okay. So here we'll have take suppose T0 has given some information, we will project it to T4. T1 has given some information, we will project it to T4, T2 has given something, we will project again to T4, like T3 to T4, and T4 itself we have got some data. So, everything that you are getting at T4, you can just try to kind of average it out. In this particular case, everything will add up and then divide it by 5. Okay. Then that will be a much better information compared to what information we have got only at T4. Because this noise averaging is not happening otherwise actually. Okay. And then from T4 to some finite window, we'll keep accumulating. So, that means up to here it is let's say T0 to T4. Then here when you go, we'll have this 5 data, one more data averaging, then one more data will accumulate. So, then after a while, we cannot keep on accumulating because there will be too many data actually. It also makes sense to kind of remember the most recent data rather than getting reacted to the very data that appeared very far away. So, we don't want to do that because recent data is supposed to be much more accurate and things like that. So, what you do here is there is a accumulation loop, okay, I mean there is a guidance closure loop. This is where the missile just flies with open loop, no guidance in action. Then further there will be some sort of accumulation averaging and all, and missile will start reacting to that after that. And after a while there is a finite window and that finite window will slide actually. Okay. In other words, once there is one more new data will come, the very first data will be ignored actually. The recent data will be kept and the very last data will be ignored, and then the window will be sliding actually. And then you do all sort of averaging, okay, then you take it. That means when you talk about T10, let's say, then what is happening here is T0 is projected to T10 in a prediction mode. T1 is projected to T10, T2 is projected to T10 like that actually, and everything happens at T10 gets averaged out, everything add up and divide by 10. Okay. Alright, so that becomes the target information, and based on that information we guide the missile actually. Okay. So, this is all explained in wordings and all that. 2 types of averaging. First is open loop, then there is a closed loop, and then all these pictures will tell you. There will be open loop, there will be accumulated averaging up to T0 to T9, then there will be sliding averaging in operation. And this operation ceases a little bit before the real T go basically. Because towards the end what you observe is if the data has not been corrected by that time, then there is very less time to do anything actually. So, it does not do very good job actually after that. So, we leave out a little bit time before TF where we just simply operate on the prediction mode. Alright, so this is what you see after doing this. Okay, remember this is not a straight line anymore, but this is a little bit jittering here, and this is the information as seen by the seeker information actually. Remember, the real target can go still in a straight line, but our seeker will keep on telling that something is like this actually. But that does not matter, it still operates based on the information that we have, and towards the end, remember, from here to here there is no further information actually. We just operated based on the prediction mode. In this kind of logic, the missed distance happens to be 0.3 meters, very small, and then if you see this the averaging and all that, so the different values of the mist distance, okay, these are various things. So, okay, we take various random cases and all, and then average it out and see what happens in some sort of a Monte Carlo sense actually. So, you can see that the maximum mist distance that we obtain is about 4 meters here, which is very small. So, in conclusion sense, it is actually a partial IGC is some sort of a new philosophy. So essentially what happens here is the inherent timescale separation property between translation and rotational dynamics is exploited, and hence it leads to better performance with lesser and smoother control effort actually. Okay, with minimum control effort, a very small mist distance is obtained. That means it results some sort of a hit to kill capability of the vehicle, and in a way it our claim is it happens to be better than both conventional design as well as the one loop IGC designs actually. Also observe that ZDM plot is very well behaved, and information required for implementations are available and successfully verified for different perturbation cases, so without any separate case to case tuning sense. And then somebody thinks that okay, this MPSP SC cannot be used as such, then because they still operates on iterations and all that, still you can have some sort of finite iteration operation. And that also we experimented with just one iteration at a time, and the results were very good actually. So, essentially it leads to very less computational time as well. Okay. So, the summary is PIGC with the DI and NA in the inner loop, this neuroadaptive in the inner loop, it also gives us a lot of robustness for parameter uncertainty and all that actually, without compromising on the performance too much. So, again the references are like this. Any of you are interested, you can see some of the references and get more details out of it actually. That's all for this lecture. Thank you.